This is our final brief foray into the wide world of optimization inside programming. Here we'll finish off our exploration of the return value optimization, and we'll also go on to briefly consider the notion of inlining and to look at the cost that's associated with actually invoking a method, so we understand that. But first things first, return value optimization. As mentioned in the last video, we ended up saying that temporary variables, R values, can be created whenever we are executing or whenever our code is being executed. It's important that we understand the conditions under which they can be created. And RVO, return value optimization, is a particular technique that compilers can use to avoid unnecessary temporary object creation. But we have a role to play here in terms of actually enabling the compiler to make use of this particular form of optimization. So just by way of, again, setting the scene on this particular one. So RVO is commonly used by compilers to avoid needless temporary object creation, particularly when an object gets to be returned by some function or through some particular process. So here we have an example. You can see if we're in the code fragment on the right hand side of the screen. At the very bottom, we're creating a new foo instance by calling a method create foo, passing in a value 6, doesn't really matter. Just above that, we have our definition of create foo. There in line 3 in that, we're going to return a new foo instance with a value passing in the parameter. Now, that's our R value, that's our temporary variable. We have no way of referring to it as a programmer. It's just simply returned as a nameless object, and then will be assigned, copied across to foo itself. And inside foo, we're assuming we have a constructor that can accept it in by way of enabling this to be built up. Now, at the minute, the steps that we would go through for doing this, we'll call create foo, fair enough. Inside create foo at line 3, we're going to create a temporary object. That's the thing that we are returning, and it's going to be instantiated using the particular value we pass in, 6 in this instance. So they return the temporary foo object by value, because that's in C++ how it would be done. And then use the copy constructor, so there we're doing the copy assignment constructor, to copy the temporary object into foo. So we're copying it across. So that has the risk of creating a temporary variable. Now, for compilers that are set up to support return value optimization, most of the good ones will be, then you will avoid the need to create that temporary variable. Effectively, what they do is they say that because foo is in the process of being constructed, it hasn't yet been constructed. And because I am constructing a temporary object that I'm then going to assign to this other object that I'm trying to construct, I can effectively just construct foo directly. So in essence, foo then becomes the temporary object. So it is constructed directly, doesn't need to be copied across. So we avoid that unnecessary generation. That makes perfect logical sense, but we need to be cautious and careful that we don't inadvertently create it so it already exists, in which case the compiler can't do that. And here we have an example. So at the top is the good form that we want to have. So we're creating 2 strings, well, actually 3. It's got first and second being created the first 2 lines, and string S3 is equal to S1 plus S2. Now, that third line, it declares S3 and also creates S3 at the same time. So whenever we have S1 and S2, we've got a temporary object being created. It's being created by way of actually creating S3. And RVO then can kick in by way of the compiler saying, look, I need to create S3, that's what I've been asked to do in that line. I have this temporary object I'm going to create anyway, I might as well just use that for S3. So it knocks the 2 things out. The example underneath is more problematic because there in lines 1, 2, and 3, we are creating S1, S2, and S3. So S3 already exists by the time we get down to line 4. So in that case, we have to create a temporary variable so that we can then copy the contents of that across into S3, because S3 already exists at that particular point. So it's better to write it in the first form, that we are constructing it in a way where things like return value optimization can be used to help speed up the process of construction. Little piece of general advice here about passing in parameters. This applies more so to C++ than it does, for example, to Java, though there is some application to other languages like C#. So objects should rarely be passed by value to a function or method. So for passing things in, and we'll see this when we're looking at calling a method, we've got to copy those parameters. So if I'm passing in an integer to a method as one of the parameters, I have to make a copy of that int, so it then can be a local parameter within that method call. If I have an object being passed in, and because in C++ objects you can pass by value, or you can pass them as a pointer to a location, if they're passed by value, I have to do a copy of all of the content of that object. And depending upon how much memory that object actually allocates, that can be a reasonably heavy cost. So ideally, if we're passing in objects to our methods, we should pass them by reference. That, in most instances, will be faster. And the principle of least privilege or least access most certainly applies here. So if you're passing in an object by reference and you know that your method is not going to change that thing, it just wants to read the contents of it, make sure it's a const reference by way of enforcing that and making it clear to anybody using that method that it's a safe thing for them to do. I want to finish things off then by looking at the notion of inlining. And before we get onto that, we will briefly have a little foray into what happens when you execute a method and the cost that's associated with executing a method. Because calling a method, it is actually a reasonably expensive operation. There's a reasonable amount of cost involved. Now, to do that and to understand that, we also have to break it down a little bit to think about how a program is executed. And to do that, we have a number of pointers or things like this that keep track of where the next instruction in memory is going to be found, or whereabouts in the stack we have stored data. Now, depending on the platform you're running on, there can be different ways of doing this. What you see in this slide, it's a reasonably common setup. So when executing code, a number of important housekeeping registers are employed. So these are things that keep track of how we are executing, enable us to execute it safely. So you can see three of them here. One's the instruction pointer. So the instruction pointer points to a bit in memory that tells us the location of the next instruction that needs to be executed. So it's the address of the next instruction to be executed, invoking a method. So if we call a method, then you're basically changing the flow of this. So a method will change the instruction pointer to the start of where its instructions begin. When a method ends, we have to be able to return to the point at which we called it so we can carry on execution. So if you're invoking a method, you've got to save your instruction pointer so that when that method finishes, you know where to carry off executing code from. So invoking a method saves the current instruction pointer as the link register, as the LR. We'll look at that in a second. And then updates the instruction pointer with the address in memory of that method's or that function's instructions where they begin. So in the middle we've got the link register. So it contains the return address, the instruction pointer of the method that called the current method. So it means that whenever you're calling something, you have a way of going back to the point at which you called it and carry on execution from that point. What happens if a method, you call a method and that method calls another method itself, and so on? In that case, perfectly fine. If a method is being called and wants to call another one, it will push things like the instruction pointer, the link register, onto the stack. So it makes a saving of this in the stack so that whenever the method that it calls is returned, it can take out its original link register. So again, when it finishes, it is able to back out to it. So these things are saved. Stack pointer as well. So it tracks how much of the stack is being consumed, fair enough, to hold local variables associated with that particular function or method call. And again, if you're calling another method from inside a method, you've got to save your stack pointer on the stack so that whenever control is returned to you, you're able to work out, well, you know how much memory you had allocated on the stack. You've got a record of that. Now, but cited in the bottom, there can be other things like frame pointers and so on, but instruction pointer, link register, stack pointer, they give you an indication of some of the things you need to save if you want to be able to call methods and to revert back and to carry on and to understand where you left off from. So roughly speaking, if you want to call a method, here's some of the things that can happen. So a method invocation sequence can be similar to the following. The invoking method pushes the arguments to be passed onto the stack. So if I'm calling a method and I have to pass in some arguments for that method, parameters that go in, then I'm the invoking callee. I know the things I want to pass in. I push them onto the stack to make them available then to the method that I'm calling. And the stack pointer then maybe will point to the start of those arguments. I've got to also push the returning instruction pointer address. So whenever that method finishes, I'm going to say, right, well, I was calling you, here's I want return to control, or the control to return to once the method has finished. So I also push the instruction pointer or link register onto the stack, save that as well. The invoking method, depending on which registers it accesses, if it wants to do things cleanly, it may also save some other registers as well, so that when it is finished, it can revert back cleanly to the previous state that things were in. That does depend upon the method. So all of those things have to happen to call a method. On the other end, on the return side, whenever the method's done whatever the method is set up to do, and we want to return control back to the callee, then what do we do? Any return value is stored to be accessible to the invoking function. So if we have a return type, we need to store that in a location where we can get access to it for the returning method. If we saved any registers onto the stack, we need to repopulate those. So we are basically returning to the state in which we were called from. And then for the instruction pointer, we'll take that off and we will carry on executing instructions from the callee's address where we originally called from. So that undoes effectively all of the things that we got pushed onto the stack that we recorded. Now, the key thing I suppose to note in all of this, if you're invoking a method, it's not, there's work involved in doing that. And depending upon the number of parameters and things you need to push in, it could be 25 CPU cycles, it could be 100 CPU cycles. There's a reasonable volume of work. It becomes an issue if you have a method that doesn't do very much. Maybe it can be very important, but in terms of the number of CPU in cycles, it doesn't require too many cycles to do its work. And if you're calling that method frequently, it means then that most of the CPU time is actually being spent in setting up and calling the method and backing out from calling the method, not doing what we would perceive as sort of useful work in terms of contributing to what we're coding. So we want to have a way then of, for small pieces of work that we frequently do, of being able to execute those without incurring a lot of overhead. And that's where inlining comes in. Now, there is an inline keyword in a number of languages, including C++, and quite often compilers will try to do this anyway, behind the scenes, in terms of working out where they want to inline material. So the inline keyword suggests, and I say suggest because most compilers, it's a suggestion to the compiler. It's up to the compiler what it does. That for performance reasons, the method should not be called, but rather its instructions directly inlined. So what this means is, even though I've written it, where I'm calling this method, if I've defined the method and I'm saying I want this method to be inline, anytime we are calling it, we don't actually call it. We basically take the body of the method, the work, and we paste it into that location at which we were going to call it. Now, that means we're not incurring any method execution costs because the stuff is directly pasted in. The cost to this, there's always a cost, is that if I'm calling the method 5 times, now before it was a normal method, I've just declared the method once, I call it 5 times, there you go. Now I'm actually copying the code, the instructions, and pasting them in 5 different locations. So it increases the memory size associated with it. So it's a notion of invoking it, of pasting in those instructions every single time I've ended up calling it. Depending on the size, the number of these, again, it'll increase the memory footprint. So there's a trade-off in this regard. But at the bottom, particularly in relation to C++, other ones too, it's an instruction to the compiler that it may want to do this to look at it. But good compilers will do this routinely anyway. But no harm, I suppose, in us as programmers trying to get across our preferences of what we think, based on our understanding of how it'll be executed and called, should be inlined. There is sort of a rough guidance, a bit of table here. So we've got call frequency going down the, you see it over on the left hand side going down, and then sort of the object size or the method size going out across the top. So for call frequency, we're saying if something is in the bottom 80% of methods, it's low frequency, medium, top 5 to 20% of methods, high, top 5% of methods. And again, the reason you sort of have this overall split is that in most programs, the majority of time will be spent in a small number of methods. That's generally the reality. It's the common path, the things you do time in and time out. There'll be a large number of methods which will be called every once in a while. So generally speaking, for inlining and things like this, you're only interested in the methods that you frequently call, and there's generally a small number of those. The bit at the top is a way of trying to measure the cost or the amount of work associated with that method. Now, it's expressed here in terms of number of lines of code. That can be big, greater than 20 lines of code, medium 5 to 20, small 5-ish lines of code. This is too crude a measurement. You really need to sort of look at this more accurately, because if a line of code that calls another method, that has implications. Some lines of code actually, in terms of the instructions that you're doing, can take more time than not. So basically what we're trying to break this down to say how much work needs to be done, and there's different ways of measuring this. So if it's a large method, a large amount of work, and you only call it every once in a while, don't bother with inlining. Medium, don't bother with inlining. So if it is a large method and you are calling it very frequently, so you see at the bottom, consider rewriting to expose the fast path and then to inline. This is basically an indication that if it's a big method and you're calling it frequently, you probably don't want to be pasting in a big method all of those times. So you should look at that method and to work out, is there a common path? 9 times out of 10 when I call this, am I doing A, B, and C? And I'm always doing A, B, and C. And is the rest of the code sort of stuff that is occasional? Sometimes I do this, sometimes I pick up on that. Now, it may not be the case, but you're looking at it and you're considering, is this the case? And if it is the case, then there's merit in rewriting that to have a small method you can inline that has the common flow. And then you're having other approaches which you wouldn't bother inlining for the more exceptional stuff. Similar for medium then, if it's low, generally don't need to bother about it. Or low frequency, if it's medium or high frequency, then you should consider, okay, well, how often do I need to paste this in? Is there any opportunity to restructure and refactor this to expose, if you like, the common path, and then to optimize that directly? For a small method, a small amount of work, if it's in the low frequency, it's up to you. It's not going to make much difference one way or the other. If it's medium or high, then you really should inline. There's good reason to inline that, because you'll get a good performance return, particularly for something that's frequently called. So there's no reason why you wouldn't want to inline it in that case. So by way of key takeaways, and these are a couple of very generic ones here. They're not necessarily specific to this, but sort of tied in across all of the optimization talks. A lot of the things we've looked at is about balance. And it doesn't matter if you're talking about optimization, where you're trying to balance performance versus memory usage, where you're trying to balance sort of design extensibility and flexibility versus some enhancements that can maybe be faster but limit that. But there is a balancing act in all of this here, and the general advice is, particularly for code optimization, that you look at where it's going to have most impact and you consider those particular points. Of course, if you get the design right, you've gone an awful long way to actually getting it working overall. Here's the mantra: use a solution that's as simple as possible, no simpler. That's good Sage advice. well, for thinking about structuring code, either in a way that the compiler will be able to optimize, or in a way that's going to sort of fit on well into memory, is useful thinking about this, and it's useful trying to have a solution that is as simple as possible so the compiler can understand it and can apply its optimizations. But yet, sometimes complexity can come in if you want to think about how it's set out in memory, and you may there find yourselves introducing a structure where you increase the complexity, but you do so in a way because then it makes it more localized in terms of the memory locations. So very much, there's a lot to take in. It's all about balancing things out. Try to keep these things into mind. Make use of a profiler. It's those types of activities that will help you write good, well optimized code.